So for this video, I will talk about support vector machines. It's a statistics-based method, but also has a really intense topics in optimization. And we can use this method for classification. For today, I will talk about mainly for binary classification, but of course you can easily extend that one for multiple classification in here. And so what should you know is in here is that, so we will use basic geometry. That I will assume that you know that basic geometry beforehand. And the optimization, this is a real optimization motivated method, but it's just an introduction level, okay? Don't worry if you have a little information in there. And then we should know that names of Ninja Turtles because my example is going to be in that topics. And here is what. So you have some ninjas, and when you see a new ninja and that it encountered to your room, and then you want to put that one to one of the classes in here. So you have two main labels or classes in this example, purples and orange ones. I think they are Leonardo and let me see what they are. And the purples are Donatello and oranges are Michelangelo in here. When we have these guys, we are trying to add a line between them, okay? Let's assume that we have two labels, and when we have two of them, then we can use only a line in here as a separator of these two groups. And when there is new one, sorry guys, when I have a new turtle around here, I just want to put that one into one of these areas in here by using my line in this example. And let's move to a new example. We have minuses and pluses. We are more familiar in this kind of two-dimensional spaces from math and geometry and statistics. And let's say I can add a line between these two classes in here. It can be a purple one around these guys, okay? Or, and let's say this may be too close to minus in this purple, in this example, then I just get rid of that one and add a new line in here. So there may be infinity number of lines between these two guys in this example, and we will try to find something like a best one, okay? And so the question in here is that which straight line should I use? Okay, you already know that there are millions of lines like that one, but I should find the one which is more useful for me to separate these two classes in this example. So which one I should use? Here is the answer actually in here. We will find the widest road, this road that separates the two groups. Please keep in mind that in this example, we are assuming that our classes are separable, okay? They are easily separable in these examples. And so we will try to find that line, and the rule is that the widest road that separates these two groups in here. And now we will talk about this root as margin. I have my widest margin in here. And these terms are kind of important for us guys, for this method, because when you try to read or watch about these support vector machines or similar methods, and they're not calling them rods, and you will heard them as margins in there. And it's kind of easy for us to just know the meanings in here. And then let's move on. And these are the two guys. And the distance between the points and that line are as far as possible. So you want to have these two guys, the biggest one, and from this guy and this guy, and you want them the close closest one to your vectors, we will call them as support vectors, and then widest road in here. These are the rules, and now we will know the distance between the points and the line are as far as possible. And here is what the distance between the support vectors. Let's say these two guys are my support vectors, and the hyperplane as far as possible. Okay, what do you mean is now we know this margin and we know our support vectors, these two guys, they can be one or more than one in here. For example, I may have another point in here or here or here or anywhere around here. Okay, and this guy is my hyperplane, and I want them this distance from support vectors to hyperplane as far as possible. These are my general, or these are my main rules for this method. And here is what. And this hyperplane is the one that just best splits my data. And I'm just looking for this guy now. And this guy is as far as possible from these support vectors that we already talked about them. And we maximize the margin. That means we are just maximizing that margin between my support vectors and my hyperplane. Here are some examples in here. And in support vectors, you may have some small margin and large margins, and depending on your data sets in here. It is kind of a data-oriented method in here, and your margin is just depending on how your data is located. And also sometimes we will use some data sets and they're not going to be separable, but as a starter, I'm just assuming that I can easily separate my data sets into two, okay? And so how we can maximize that margin? How is it possible? And so there's one method that is maximal margin hyperplane, which is the separating hyperplane that is farthest from the training observations. And for most of the machine learning methods, we will use our training data sets to run the model in here, even it is a maximal margin hyperplane or support vectors or any method we are using there. And after that, we will use test data to see the performance of our classification method in there. And then we can compute the perpendicular distance from each observation to a given separating hyperplane. And please remember that this distance, maybe you can remember from the geometry, this distance is the closest distance from our observations from the hyperplane. That's why it is important for us. And the smallest such distance is the minimal distance from the observation to the hyperplane. And we know them as margin in here. And we can then classify a test observation based on which side of the maximal margin hyperplane it lies. And we call them as maximal margin classifier. So this method is just starting with maximal margin classifier. This is the basic one. Then we will extend that to the support vectors or support vector machines. So let me move on. So this is, I just wanted to add a friendly note in here. Where if you want to use SVMs, they are really good for small data sets with fewer outliers in here. And also, and if you have more data, you can use random forest neural networks in here. And please keep in mind that sometimes it is not easy for us to classify when we have small data sets. But when we think about SVMs, it is really working well in these data sets. But if you want to work with like random forest neural networks like boosting and bagging methods in there, generally they are requiring more data sets. Please keep in mind that one too. And so what is a hyperplane? We should first talk about this guy first. And in a p-dimensional space, a hyperplane is a just flat affine subspace of dimension p minus 1. Okay, and the affine indicates that the subspace need not pass through to origin in this example. And let's see an example. If you have 2 dimension and your hyperplane is just a flat 1-dimensional subspace, and actually it's a line in there, and we can just define it by this equation in here. And this is really similar to regression line, but let's see, this is equal to 0. And when we think about our linear regression, it's equals to your response variable or label or your target variable. And here is some examples. These are just separable data again. And so if you have an hyperplane in Rn, and you will have n-1 dimensional subspace. And let's see, we have 2-dimensional subspace, and our hyperplane is just a line in here in R square. And if you have in a 3-dimensional space, then your hyperplane is just the plane in here. These are the visualization that we can see, some hyperplane examples. And let's start with that math representation of our SVM and hyperplane. As usual, we have the data with xi's and yi's. Xi's are our variables that we will use for classification, and yi is called as labels in support vectors, okay? And we call them as a target variable in machine learning generally, and response variable in statistical methods. But when we are in SVM world, and we just call them as labels, okay? And for these labels, there are kind of special labels for these examples. They are -1 and +1s. That means we are in the world of binary classification for this example, okay? And we are in p dimension. And the idea in here is that we are separating the data points into 2 classes with the help of a hyperplane. And here is how we can define that guy. We have axes in p dimensions, and we will use that affine subspace, and we will to separate our data sets in here. And this is a supervised learning method. And then this, and also a binary classification. I already talked about that. And here is how we can show that one. And this following equation and can easily be expanded to the p-dimension setting in here. And here is our example, and let's see how we can extend that guy. And so we have this hyperplane with this equation that we will define it with this guy, 1 plus 2x1 and 3x2. And we are in 2 space, and we have some blue dots and pink or purple dots in here. And that means we have 2 classes, okay? And we are just separating these 2 planes by using one hyperplane in here. And if this hyperplane is greater than 0 in this example, we are in this area. And this is the geometric explanation of our equations in here. And if that guy is smaller than 0, then we are around here. Okay, this is how we are talking about that part. And these are the examples. You can see them in like that. You have X1s and some purple and blue dots in there. And you can use several types of separator in here. And then when you add one of them, that means you just split your area into 2. And when you see a new data point, like a test data sets, like if it is around here, you will just say that my new observation is just belongs to the new class in here. So let me move on. And so we are again in our p-dimensional space in here, and we added our hyperplane in here. These guys are support vectors, And then we have our margins between these support vectors in here. And then if in this area, our label is as 1, and in this purple area, our label is as -1 in here. And then here's how we can define our hyperplane, beta transpose x plus beta 0. And so please remember that if you want to move a line to the left or right, you can just add a delta or a small number in there to move your line in here, okay? And if I just move to the left from my hyperplane in here, I can just say minus delta, and then this guy is going to the left, and then if I add this delta, and it is going to move to the right in here, okay? Since I'm going to just trying to define this part in here, and let's say if my equation in here is smaller than delta, I'm going to be this area, and if it is small, so greater than delta, I'm going to be in blue area in here. And if my equation in here, my affine subspace is smaller than delta in here, then I'm going to be in my purple area. And here is how we can explain that one. So we can say that each observation is on the correct side of the hyperplane and at least a distance delta from the hyperplane, okay? So we want to have that one. We want to have our observations on the correct side of my hyperplane, and we want to have at least a distance delta from that hyperplane in here. And we can just choose beta and delta, which is going to maximize the two planes which are shown as. So please keep in mind that this margin in here, let's see, we have a margin here. We want to have that guy as big as possible, okay? For each aim in support vectors, I will have that margin, and I want to have this one as big as possible. And I will just maximize that guy. And here's how we can define it. And then we are going to choose that betas. And please keep in mind that x is just observable data. We know them. These are not parameters in here. But these betas and beta zeros are just our parameters in this example. And so we are just choosing that beta and delta is going to maximize the two planes in here, okay? And if I divide two parts or both sides to delta, nothing will change because these guys are just 0, and I can just divide that, or even it is not 0, nothing will change when I divide both sides into delta in here. And then to make it more easy, to make that calculation more easy, we will get that delta as 1 in this example, okay? And here is this part can be explained like here. Let's say, please remember this guy in here. Let's say if my equation is greater than delta, I'm in the space of yi equals 1, okay? By looking at or remembering at this part, we can just write this part like here. I have my x's, my observations, and my labels. And when my label is equals 1, then here is how I can define my equation. And then if yi is equals -1, then here is how I can define it. And when I just combine, when I want to combine this whole part into one equation, I think it should be not that hard to see this part is equal to that part in here. Yi times beta transpose xi plus beta 0 is greater than 1 in here. Okay, you can easily see that part. And here's how I can see that one onto my two-dimensional space in here. Let's see, I have my beta 1 and beta 2. And here is my aim. Please remember that part. I'm going to choose beta and delta, and it's going to just maximize these two planes in here. Okay, we already divide them to delta and take delta as 1 to make it more easy. And here is my subspace. I have my subspace is just going through 0 in here, and beta transpose x equals 0. And let's say I'm adding beta 0, and then now I can just move my line to the left, and then I can just add or find a point in here, and this vector is going to be my x bar vector in here, and I can just add a perpendicular line to that one. And please remember that this is going to be solution of my equation in here. And here is my beta in this example. And then please keep in mind that this beta is perpendicular to beta transpose x, and it is also true for these two guys in here by looking at this geometric explanation of that one, okay? And then let's see them in here too. And I'm also adding beta transpose plus beta 0 minus 1 line to here. And then another point on my x bar, and just having a vector from 0. You can take any vector from here, but if you get them from 0, then it's going to be more easier to implement. And then I'm going to have a perpendicular beta to my line in here. And now there's another theta between these two guys, okay? And you should know how to find the norm of this line in here. And please remember that, and this is how I can find this norm of this line in here. So now we will move to the next line. We have another one again. Then also we are adding our x in here, x bar, and a line from this point. And then when we add another beta perpendicular to our line in here, then we are going to find this norm, okay? And we have that guy and this guy in here. When you just combine these two, please remember that the difference between these two lines is going to be our something like an objective function in this example. And let's see, we want to find the distance between these two planes, okay? We want to find the distance between these two planes because it is our margin that we are looking for that has to be maximum in support vectors. And it's very easy to see. The distance between these two planes is equal to 2 over the norm of the beta, okay? And so we already defined that part. And now our job is more easier. And we want to maximize this guy in here. But if you do not have any constraint in this example, then you can find like millions of or infinite number of solution for this maximization. But please remember, in support vectors, we are trying to just classify our training or test data sets in there. And that's why we have something like a constraint in these examples. And then we are trying to maximize this guy subject to this guy in here. So to maximize this guy is equal to minimizing that guy in here. It is kind of easier to minimize. And we still have the same subject to equation in this example. And then I can write this part like here. This is a quadratic form of norm. And please remember that this beta is a vector. And we can just write the norm of the vector as a quadratic form in this example. And now I want to minimize that part subject to this equation in here or inequality in here. And so please remember that this mathematical model in here has a quadratic and convex objective functions in here. This guy is just quadratic form, and it is also a convex objective function. And then you can find the minimum point in for that one. And our constraint is just a linear one. when you just look at for this beta transpose and beta 0, this is just a linear one. Of course, you can think that I have yi times xi in here, but please keep in mind that they are just non-data sets, okay? The unknowns are just betas, and that's why they are linear constraints in here. So since we have that convex objective function and linear constraint, we can say that now we are facing a quadratic programming model in here. And here is some example in here. For this data set, I can easily separate my data with a line in here. But when we move to the right, so if I have another point in here different than this guy, now you will see that this line is really changing. My hyperline is now a really different guy than that one. Okay, so we should be careful for these kind of situations. Also, we should be careful that I may have some purple lines around here or blue, purple points around here or blue points around here. That means I am not that separating my data that easily. And here is how I can show that one. Please keep in mind that now I'm talking about not separable data sets, okay? So far, we were just talking about separable data. So let's say I again have my affine line in here, and then I'm just moving that one to the left. And this part is just showing me that inequality in here. And again, I can talk about this A part. This is a very easy part that I can write in here. I already know that part. But this time, I want to add an epsilon, like an error in here, and to make sure that I may have some of my observations in this part, or like some purple points around here. And also, I can define that B part, like here. Let's say I have small epsilons. In my A part, I don't have any epsilons in here, which are 0. But in this B parts, I may have some epsilons between 0 and 1s. That means I have small ones. And also I can define that C parts, depending on this guy in here, for higher epsilons in here. Now, when I add that epsilon to my equation, I'm talking at that not separable data because now I can make some errors in my equations in here. And then let's talk about this one too. I have another line, which is smaller than -1. And then I can talk about this A part, which is epsilon is smaller, epsilon is equal to 0. And I can talk B and C parts very similar to the previous one. But now my label is -1, okay? So we are going to combine these two guys. And I have this part in blue and that part in purple. Now we already know that this margin equals to 2 over the norm of beta in here, okay? And now I can write or combine everything on the same equations for all areas in here, okay? Instead of the previous one, I'm able to define my constraints by adding my epsilons in here for some values of epsilon. And this is called as soft margin. We are adding some soft margins in here. And now, instead of quadratic function of this one, we are maximizing that guy. And maybe you are familiar this part with some methods. You already know some lasso and reach. And this part is really similar to that one. And generally, when we are using that epsilon, this D is going to be 1 and 2 in here. We can just maximize that part. And if you are remembering that lasso, this C is behaving like lambda in there. So now we have this C in here, and if this C is really big, then our penalty is big, and it's going to force our epsilons to be zeros in here. And now we will just maximize this part, similar to the lasso or ridge regression. We can think this C as our hyperparameter, and we can easily use cross-validation to find this C in here. And please keep in mind that this maximization is not that free. We have some subject in here, okay? We will maximize that guy subject to this equation or this inequality in here. And yeah, we can just find the C by using cross-validation. And mainly this D is taken as 1 or 2. And here are some examples. You can just look at them and think about how these margins is happening. For example, in here, we have really large margin, and then that means we have really big epsilons in here. And for example, for this guy, we have some small epsilons. Just think about these data sets. We have different margins in this example. And also, I want to tell you something about kernels. Kernels is really another topic, and it's a really big topic, and it can be used for support vectors, or you will see them in several methods in machine learning or statistical learning in there. And for example, if you have this type of data, let's see, you have some purples around here and some blues just there in there. And if I use a hyperplane like this one, and just say that my purple area is this part and my blue area is that part. And if I use that separator in here, it looks like that it is not that successful for these data sets. And for this example, instead of a line, we can use some kernels and just change the dimension of the space in here for my data points. For example, I can get that purples and just carry them to the another space and just add a plane between that guys in here. Okay. And let's see how it is working in here. We still have the same minimization problem subject to that guy in here. And please remember that Lagrange function is just found like maybe 500 years ago in here. Now I can just define this optimization by using Lagrange functions in here, okay? And now I have my lambda I, and let's see, these are just Lagrange multipliers, and these lambdas are just unknown parameters for each constraint, okay? These are just adding for each constraint in here. And here are my optimality conditions. Please remember that if I want to maximize this part or get this optimization, I'm just getting the first derivative of my function in here and just make it equal to 0. And after that, I'm going to find my betas. And also, I don't have only betas, also I have my beta 0 in here. And after that, after getting, and please keep in mind that this solution is just a vector. And after that, I have to get the derivative of my function by respect to beta 0. And then that guy is equals to 0. And after that, I can find my solution for this one as here. And this equation is going to give me a scalar instead of a vector in here. And then, and it is not that hard to write this guy to go and just write instead of betas and beta 0. And then you will find this one, okay? After that, your Lagrange function is something like here. And if we are moving to the kernels, and these dot products are important for us, okay? We are going to play with this dot product because please keep in mind that they are our data sets we are using for classification in here. And then instead of using directly these dot products, I'm going to use some kernels and just extend my data sets and carry that data set into another space and then use that one. And here is how it is working. I will just play with these dot products in here and or inner products. And then we are just replacing that part, that inner product with a kernel and which is going to just measure the similarity between two data in higher dimensional space. Let's say if you use a linear kernel, that's what we are doing so far, and you just have that one. And if you, or you can just use a polynomial kernel, and then you can just carry your inner products to another space in here. And or you can just use a radial kernel. And we just added 3 most common examples in here, but of course there are several of them for kernels in there, okay? And maybe if you are familiar with that normal distribution in there, and this is just going like a bell shape, is behaving like a bell shape in here, you are kind of moving that guys like a bell shapes in your data sets. And these are the kernels that you can use to carry your data into another space. And here's an example. And these are 2 examples. Let's talk about this one. And as in the examples in here, we are just having an hyperline instead of a line. This is just something like this guy. And we use one of the kernels and carry that guys in another space. And here's how we can see it in a better way, I guess. We have p-dimensional space. Now, using this kernel for my inner products, I'm just moving them to q dimensions, okay? This is a higher dimension than p. And let's say I have 2 dimensions in here. By using my kernels, I'm just carrying my blue dots to up there. And by using that plane in here, I can easily, sorry guys, separate these 2 classes in here. And here is what we are talking about. This is a polynomial kernel. When you use that guy, you can just carry in your 2-dimensional inner products to 6 dimensions in here. Then you will use that guy after that for your classifications. Okay. And here's where you can use your SVMs. You can just use that for classification or regression or time series predictions, or it is even used for outlier detection and for clustering too. And you can say that it's really useful methods that you can just extend that one for several methods in there for supervised or unsupervised methods in there. So we will do an example in here for the implementation of SVM in Python. And I'm going to use the Colab for this example. And then in this example, we will just use the Skylern library in Python. And then we will try to just recognize that images of handwritten digits from 0 to 9 in here. Okay. And so first of all, as usual, we will just load the libraries in here or packages that we will use for today. And here are the ones. And we will use that Skylern dataset library and just load digits is our data sets we will use. And it is just including this 8 times 8 pixel images of digits in here. And then that image attribute of the data sets, and it stores 8 by 8 arrays of grayscale values for each image. And we will see one of them as example. And please keep in mind that, of course, there are, since there are digits from 0 to 9, we have 10 classes in here. And each of them has almost 180 samples per class. And then your total sample is just something like 1,797 with 64 dimensional, since we have 8 times 8 pixel images in here. And now we just loaded the data sets and we just import SVM, and we will use some metrics for some confusion metrics and classification method, and we will use train test splits, of course. And then for some plot, we will use matplot libraries in here. And after that, let me just load the data sets in here. I will write it as numbers. and we can just add load digits for here, for this example. And X is just my numbers.data, and then it will just get it from my numbers. And Y is just my target variables. Okay, and it's going to get that one too. And now we loaded the data sets, and let's see one of them as an example. Let's just write as, or I can just get this part from my notes. And here is one of the examples. We will just use that plot and just see one of the images in the data sets. We will just see the first one, for example. When I run this part, you see that one of the images in here is seen like that. Maybe we can just assume that this can be a 0 in here. And I want to see the third one. Let's see. And this is 1 and the 10th. And here are some examples that are just including like grayscale values for each image in here. Okay, and they are just 8 by 8 pixels, as you may see also on the plots in here. And let's write the modeling first. I just want to write the modeling. I'm giving it a name as SVM, and the SVC function can be used in here. C equals 1. You can just see how they are working for this example. For this is just float, and it is just regularization parameter, and we will just use the default one in here, and it's kind of a penalty in here. And I'm just going to use kernel as linear kernel for this example. Okay, you can just play with that part too. And I run that. And now I want to split my data set into train and test data sets in here as usual. And we are having at X for training and test and Y for training and test. For this one, we will use X and Y values. And test size is 0.2. That means 80% of your data set is going to be in training. And we are not shuffling, and you can just add another random state in here. I added 3 if you have 3, and we will have the same results for our classification. Okay, and now we run this part, and after that one, we can just fit the model by using svm.fit in here, and this one. And of course, to fit your data, you are going to use training ones, okay? And we have X training, and also we have Y training for this example. And we are just fitting the data sets for SVM in here. And then I want to just get the prediction for my test data sets after fitting my model with training, and then we will just predict for test data. Let's give it a name. I say as predict test in here. We will use SVM and then predict and then X test. We have test data sets, and now we will use that one. After that, we want to see how our classification report is happening. And let's see, I will just get that part from my notes. We will print something now. And now I want to just write my classification report for SVM to see for each class from 0 to 9, we have 10 of them, to see the precision, recall, F1 score, and support in here. So when you remember that these classifications, we have some actual classes, they are going to be yes or no's, and we have our predicted classes on the columns as yes or no's, okay? And like cross tabs in here. And if you have your actual class and predicted classes are yes, then you have true positive. If both of them are no's, then you have true negatives in there. Okay, please keep in mind that. And then if your actual class is no and your predict is yes, then you have false positive. And if actual is yes and your class is predicted class is no, and then you have false negative. Okay, we have true positive, true negative as, and then false positive and false negatives in there. Okay, and please keep in mind that of course we want to have higher true positives and true negatives for our classification. And these precisions, recall, F1 score, and supports are just finding by using these guys in there. I mean, these three guys that we will talk about. And when we talk about this, let's say for accuracy that is just given in here, and then accuracy is just a ratio of correctly predicted observations to the total observations in there. And you will just use true positive, true negatives, and over all of them. Okay. And when we just look at for precision, you see that we have really high numbers in here, but maybe for 1, or for 8, it is the smallest one. And precision is the ratio of correctly predicted positive observations to the total predicted positive observations in there. That means you have true positive over true positive plus false positive. Okay. And then we have recall in here. It is another thing that we can check out. And it is kind of sensitivity, if you are familiar with this term. And it's just a ratio of correctly predicted positive observations to the all observations in actual class yes. That means you are getting true positives over true positives plus false negatives in there, and for recall. And we want to have some higher numbers for all of them. And then for F1 score, the last one in here, and it is just a weighted average of precision and recall. Sometimes they think that it's more useful to see how your classification is working. And the understanding is kind of harder than the rest of them. And so it's just, you are just having recall time precisions times 2 over recall plus precision. Okay. And then you can just check out for these parameters to see how your classification is working for this example. I think it's working really well. Then our accuracy is really high for this one. And also we can have some confusion matrix to see how it worked in there. Let me just check out for this example. I will run this part. And here is our confusion matrix. And you see these guys are just true predictions. Let's see, your label is 0. And for all of them, you just predicted them as true, okay? And let's say your true label is 1. And for like 35 of them is just true. But when you check out for this part, for some of them, it's just predicted. Let's see. Sorry, guys. And for this one, it is okay. But for, let's see, 6, when it is 6, it just predicted as 1, or 8 for 3 times, it is predicted as 1. Maybe 8 is very similar to 3, and you have some false predictions in here, especially when you have 8 as actual value as true label, and the true prediction is 28, but for some of them, it just predicted as 7, 3, or 1 for this example. Okay, and that's how we can see. And the 6 is the highest number as the false prediction. It is for 3. When you have 3, the 6 times it just predicted, your method is just predicted this 3 label as 8 in this example. And this is how we can see or implement our SVM for this load digits example, we can see the actual images in here and split our data set as training and test, and just run our model for training data sets and just run prediction for test data sets. And we can just check out for classification report for our test actual values for your labels. And then we can just check out for accuracy first, then for precision, recall, and F1 score for all of them. These supports are also can see in here and the number of classes in there. And also we can see our confusion matrix and see which ones are predicted as true or false for this example.